Let's start with problem A. In problem A, we had like the story was that we have some characters, lowercase English characters, and we are considering their ASCII code in binary. So we had some string consisting of them, and then we reshuffled the bits of like the concatenation of the binary representation, and we want to get back any string which satisfies this. So it's like any string which could generate this sequence of zeros and ones. Okay, so like we can clearly see that that those lowercase ASCII characters have like at least 3 ones and at most 6 ones in their binary description. So what we can do, we can of course, if the answer is if like the number of ones is less than 3 times n or bigger than 6 times n, then like we won't be able to solve it. So what we can do, we can in each like as long as there is anything left, we can add any character which does not violate this requirement, and yeah, and that's it. Any questions? Okay. Next problem, modulo. In this problem, we had a sequence of length n. N was up to 300,000, and we had elements AI. So what we wanted to do is we wanted to calculate the number of ways to like split our array into a segment, such that sum of each like interval, sum modulo 10 to the power of 9 plus 7. This number is even. Okay, so how do we know if like this number is even? So how do, like, looking at S, how do we know if this number is even? So my claim is that it is even if and only if and only if S modulo 10 to the power of 9 plus 7 modulo 2 is equal to S divided by 10 to the power of 9 plus 7. So like this means that if we drop or no, wait, 0. No, it's good, I think. Any like questions to this statement? Because like this means that before the first overflow, this number being odd, this number being even is equivalent to S being even. After the first overflow happens, then this number being even is equivalent to this number being this number being even is equivalent to this number being odd, because we are subtracting 10 to the power of 9 plus 7 once, right? And so on and so on. Okay. So that means, any questions to this claim, or? Okay, so what we can do, we can like maintain, because how do we like calculate it then? Let's have a dp dpn means in how many ways can we partition the prefix such that this everything here holds. So what we basically need to maintain, we need to maintain a segment tree or like two segment trees because what would be the formula? We would like to sum over all i's smaller than n and add dpi if and only if right? Well, like this notation means this notation means one if the statement inside brackets is true and zero otherwise, right? So like we want to consider all the splits. Sorry, here is like modulo 10 to the power of 9 plus 7. Yeah. Okay. So we want to basically take some out of those who connected with us, like who connected with this prefix, give us like a good sum. So what can we do? Is we can maintain a segment, two segment trees, tree 1 and tree 2. They both, what they both hold is for T0 and T1. So T0 holds some of the dp values from all the prefixes which have this equal to 0. And so like in T0 we are only considering prefixes with this expression equal to 0, and this segment tree has 10 to the power of 9 plus something leaves. I mean, obviously we cannot store it explicitly in a memory. It will be like we will store it using pointers, right, and not building the whole tree when we don't need to. So for like chosen value here, the segment tree stores some of the dp's with this sum, and this segment tree the same but with this expression equal to 1. And then what we need to do when like pulling the values, we need to just do like 2 queries on those segment trees. Questions? Okay. Okay, C was directed acyclic graph. We had to construct a small directed acyclic graph where the number of paths from 1 to n is exactly k, and there was also some other requirement. At most 2 outgoing edges. Okay, so basically when we want to construct something that there should be exactly k of it, we can usually think that, oh, it would be cool if we could multiply the result by 2 or add 1 to the result, right? Because like then using logarithmic number of like operations, we could construct exactly k. And that's the case here, because when we have something that has some number of paths to the n, we can say, okay, this n is actually not n, it's actually n minus 1, it's some like actually some t, but here we have n, and was this permitted in a task, or okay, so we can whatever, right? we multiply the result by 2 this way, right? And adding 1 is also not hard. We can do. We can say that we have a new beginning and do like that. And any questions to this? Okay. So next problem is the hamsters. So in this problem we had n texts, n was up to 200, and their sum of lengths was reasonable. I think it was like 200 each or something like that. It doesn't really matter. And what we were interested in is we had a guarantee that no pair, like for each pair of strings, one does not contain the other, and we wanted to produce a shortest text which contains k occurrences of strings from this set inside it. Any questions to the statement? Okay, so what we want to calculate is let's say that we have a text and it ends with some occurrence st, and now we want it to end like to add something, so it ends with occurrence as u. How many characters do we need to add? Okay, so this is some like trivial. This can be calculated trivially with KMP or hashes, right? Any questions to this part? Okay, so this gives us a graph, like a full graph. And now what we want to do is we want to calculate shortest path, which contains exactly k edges. Okay, so what we can think about is okay, if we were to count paths which have exactly k edges, who knows like that we have a graph, let it be directed, and we want to count paths with exactly k edges where like the size of a graph is 200. Who can solve this task? Okay, so this is pretty similar because like in this previous task we would use matrix exponentation, right? So here we can do exactly the same, but we just swap the I think it's ring. We operate because like when we are counting something, we operate in like plus multiply, but we can swap it with max. No. Yeah, with max plus, no, min plus, and it's still like a valid matrix multiplication. I mean, there is no like division in this matrix multiplication, but we don't care about it. It's still associative. That's the only thing we'll care about. So basically, what we do is we start with a vector of zeros, which basically means, okay, going like doing a path which has length 0 and ends anywhere will cost us 0 in a best case, which is true. And now like multiplication by this matrix, like literally a matrix of weights of the graph, what it does, it considers like going through every edge to every position, right? And we can just do a like fast exploitation on this matrix because like this operation is still associative. So yeah. And any questions to this part? Okay, now meteors. So in this task we had n countries and a strip of length m, and on each like position there was some like this base of a country where like m was at least n, I think. So that means that like some countries have multiple bases. And now what happens is like q times some interval, like cyclic interval, but it doesn't really matter for us, is chosen, and like each base there gets some like ki meteors, and like the country whose base is there gets to hit them. And each country has some requirement. By requirement, I mean they want to have at least xi meteors, and they want to know when will they be when will they get them. And everything is to like 100k or 100k, okay, few 100k. Any questions to this part? Okay, so what we're gonna do is we're gonna do a parallel binary search. So what it means? Because this is like clearly monotonic, so for some country, if on some prefix it had enough, then it will have enough for like the rest of the world, and if it did not have enough, then it won't have enough earlier. So what we're gonna do is we can think of it as a like binary tree. Okay, where this is like time. So what we are doing first is we are like considering this half. We run the simulation of those additions on segments up to like the half of the time, and now we check for every guy if they got enough or not. So if they got enough, they go to the left part, which means the answer for them is in the first half, right? And if they did not get enough, they go to the second part. And what we do now is we run like a simulation here, right? And then here we decide for those guys if they go left or right. Then like run a simulation up to here. For those guys, decide or left to right, and so on and so on. And like this tree has depth log, obviously, and on like each layer we run simulation once, and every guy checks once if they are good or not. So like one layer is n log n, so everything is n log squared. Any questions to? Yeah.
How many points would each have?
What do you mean? Points? What do you mean points? Like the countries?
In the segment tree, like in the first half,
You talking about this or this?
like
This? Okay, so this is just a visualization of how do we perform a parallel binary search. So like, what we do first is we simulate the reality of those meteors up to the half of the time, and then we check who already got enough.
Yes, that part I understood, but like how many points do we have? Is there an amount of points?
Do you mean like how many vertices?
Vertices.
Yeah. So we want them so that like the number of nodes here is like the amount of queries, right? Because like what's the answer? The answer is number of queries after which the country had enough, right? So we need to be able to like distinguish And like each leaf node corresponds to some updates, and those like nodes higher corresponds to like group of updates, right? Okay. Any further questions here? Okay. So next problem is fluid. Okay, so in this problem, sorry for a kind of confusing statement. I got confused by like the clarification request at some point too. I mean, clarification requests make me doubt in problem statement. So like the tricky part, I think, was to see that if we have something like that, and we put a pump here, then like the water will go down here, but here there will be no water.
Can you explain the problem statement?
Okay, sorry. Okay, so the problem statement is that we have a like two-dimensional map of some city, of like some terrain, and each position has some like altitude, and some of positions belong to the city and some do not. City is not necessarily connected, and what we care about is we want to like put as few pumps as possible to make the whole city not have water in its area, and pumps work like that they like they just like remove the water from the current position, and what it implies that like if from some position water would go there, then this position also like gets its water removed.
Okay.
So like for example here, this position also gets its water removed, but this does not. Okay, so what we're gonna do is we're gonna and up to like 1,000. Yes?
I don't understand why the water doesn't get removed.
From here? Why would it? I mean, okay, like imagine this in 3 dimensions. That like you have a wall here, but this wall is like not on a view, right? And there is a wall behind. So like, how does pumping here remove a water here?
Oh. But doesn't the wall from the
I mean, like, does the water from there get removed? Yes, it does, because like if it's not removed, then it goes like there. Yeah.
If two cells are at the same altitude.
Yeah, the water also, so like here is no water, right?
Okay, because the problem says higher to lower altitude and.
Okay, sorry for that. Any further questions to the problem statement? Okay, so what we're gonna do is we're gonna consider, we will maintain find an union, so like disjoint set union, and for every set we will maintain 2 informations. Is it being pumped, and does it have any city? Basically, then we like consider all the positions from the like lowest to highest, and like what's the motivation behind that? So the motivation is that when we are considering higher positions, and then we see that we did something in lower positions, then like if the lower positions were already forced to place the pump, then we know about it, and if they were not forced, we can always like do it by ourselves to say, okay, there has to be some pump. Okay, so what we're gonna do now is like when we are considering some position. Let's consider all the ones which are like deeper next to it. I mean, they're connected components, like those sets. And so, if this is a city, then if neither of those has a pump, we need to place pump here. Okay, I will like explain one thing in a second. So we need to place a pump here, and if like if they have a pump, we just like note in this like set union that this has a pump, right? Okay, so like the question here might be, okay, why do we put a pump here and not like deep down there? So my claim is this doesn't change anything because like this means that all the deeper levels were already considered, right? Like all the guys deeper than this. So the shallowest guy is as high as this or even higher. So if there was some guy which was to be saved by placing a pump inside, he's also saved by that pump. So it doesn't really change anything. Okay, so complexity is n squared times like alpha because final union. Did anybody have a problem with like with sort here? I mean, okay, cool. Because like on some online judges, this is uploaded with a very tight time limit, and you cannot sort the positions by their height. You need to bucket sort, like, because like the height was up to 1,000, so you need to like sort it by buckets and vectors. But like, whatever. I'm glad here like the time limit is not that strict.
I got actually like I got a memory limit by using a set. Is sorting work? If you just add them to a set, like
you did it set.
yeah.
Oh no, like
Height, position that gave memory limit.
But yeah, you mean like you're sorting an array of elements by putting them only in a set, or
Yeah.
why would you do that?
Because it was easy.
Do you like really hate having good constant factor, or?
I mean, it didn't give a time limit. It was a memory.
Okay, yeah, sure, but like, wow, that's like really amazing to me.
It was much faster to code at first because I was. I mean, I didn't solve it, but
Sort is way faster than STD set.
Yeah, because it's only a
like for multiple reasons. Sort is faster because like it manipulates data which is in like usually in a single memory region.
The cache locality.
Yeah. So okay, so like yeah, use sort whenever possible.
Yeah. That's online.
Yeah, but like also the thing with memory limit, this problem is from like 20 years ago. So like the memory limit is also from 20 years ago, and unfortunately I cannot adjust the memory limit on VJudge. Okay, next problem, depth. Okay, so okay, so we basically had two big numbers. By big, I mean length up to 10 to the power of 5, and what we care about, we care about their sum, which is like also a big integer, with roughly the same length, and we want to support the following queries: change the digit of the first guy, and the second thing is output a digit of a sum, right? Like given one. Okay, so the thing that we are gonna do is we're gonna calculate the sum like first linearly. Everybody can add two big integers here. Cool. So we calculate the sum, and from now on, whenever there is an update, which means change a digit, we only care about the delta. So like we can by maintaining those two numbers, and then like now we can express every change update as an add update or subtract update, right? Okay, and how do we do a subtraction on big integers fast or addition? So basically what we're gonna do is we're gonna have a segment tree, and in this segment tree we need to maintain like, because what's the tricky part with additions? So when you add some number to some number, cool, we get 2 here, and it overflows, so we get 1 further, right? Okay, and this overflow is always at most 1, right? So the tricky case is when we have many 9s, right? And here we have some like first non-9. So what happens now? Those 9s get transformed into 0, and this here we have +1, and this +1 never overflows because here is a not 9, right? And the other way around is when we subtract. So we get 5. 2 minus 7 is 5. But we we overflow with a -1. And now what's the tricky part here? If there is a long sequence of zeros, they transform into 9s, and here we get like a -1, right? Okay, so what we can do is let's maintain a segment tree, which in nodes maintains digits of this number, and what we need to maintain, what we want to maintain is a sum of digits in a subtree. So my claim is that we can now easily find those sequences of 9s by we can do a binary search, and if the sum of if sum is smaller than 9 times length, then it's like we are too far, right? And since numbers are from 0 to 9, this works. Since digits are from a limited range, this always works. And the same thing is with zeros. We can binary search the longest segment where the sum is 0, right? And we can do this binary search by doing a descent on a tree. So we have 1 logarithm, but this task had very low time limits. So we can do just a binary search and the query to a segment tree inside. Yeah, and so when we want to replace the segment of 9s with segment of 0s, we just subtract a 9 on the interval, right? Okay, my go-to strategy when there is a binary search on a tree is to think a few more times before implementing a logarithmic descent on a tree, because I don't know, half of the times at least the time limits are loose enough to have a binary search and then query to a tree, and it's way faster to implement. Okay, any questions to this problem?
So you have to maintain both segment trees of numbers, or just
No.
The
Just the sum. Do we maintain the just the representations of all numbers to be able to transform, because the updates were replace the digit, and we want to have updates add a number. Any more questions? Okay. Okay, so now hotel.
No.
So we had a tree of size 5,000, and what you want to count is to count a number of triples such that like pairwise distances between those three are equal. Okay, so when we have like three vertices somewhere on a tree, and we want like those distances to be equal, there must be a single meeting point, like single intersection point of all those three paths. Yeah, and what's more, those distances also have to be equal. So yeah, right. Just like from each route, run a DFS which counts the number on some depth, and then some like trivial combinatorics on that. Any questions?
Yes.
Yeah.
What if Ed was much bigger?
Huh?
What if Ed was like 6 with big power?
Sorry.
What if Ed was really big?
What if N is really big? But in this task, it is not. So like you're asking me if I can solve for big N. I think I cannot. So like I do not see immediately because like I thought about like maybe some centroids or like, but like I cannot see immediately how to solve that. So well, maybe for a reason it was set with that limits. Okay, now bridges. So in this task we had NM up to like thousands or something like that, and we have bidirectional edges, but each edge has a different weight in that direction and that direction. And what we are interested in is we are interested in some like Eulerian circuit or path. I think circuit. Okay. So Eulerian circuit such that maximal weight of an edge we are passing by is minimized. Any questions to the problem statement? Okay, maybe I should note that like this is a single edge with different weights both ways, so we need to cross it single time. Okay, so let's if we are like minimizing the maximum, we want to do a binary search. Let's have some guess and say that like some guys are blocked now, right? For some edges, we only can pick one direction. And like of course, if it's if some edge can like not be picked in any direction, then it's obviously a no. But for some edges, we have a forced direction, and for some edges we can pick. And the answer is can we do like the orientation of those undecided edges such that what? Okay, so who knows like a constraint that the graph must like fulfill for there to exist Eulerian circuit. Wow, interesting. I thought it's a very common knowledge. Like I'm not insulting you, but like just like some things are really well known in some countries. And okay, so the requirement is that for a directed graph, in degree and out degree of every vertex has to be the same. And like, okay, maybe who has a code to find an Eulerian circuit in their library? Okay, I recommend you adding it. Okay, so yeah, okay. So how do we make this? Like, how do we fill this requirement? So what we can do here is, let's say, okay. So we have some guys fixed already, and now for all those where we can choose, let's choose whatever. We don't care. And now every vertex has some balance, like. Where balance means like indeg minus outdeg, and so okay, I will spoil you. This is a flow problem. So now we have some like vertices with balances. Let's say that those are the ones who have positive balance, and like by the way, a balance is always even because. Yes, because like the degree must be even for the in degree and out degree to be equal. So those guys have some that say, okay, I have two more than I want to. I have 4 more than I want to, and I have 2 more than I want to. And those guys say, I have 6 less than I want to. I have 2 less than I want to. And what we can do is if there is an edge here, it means that we can flip it, right? Like if there was an edge here, we are only considering like the edges which are from like for which flipping them would fix that, right? And now what we wanna do. Is like we want to add the constraint here. Let me explain. Sorry. Let's divide those requirements by 2 because it means that like we need to flip that many by 2 edges. So it's 1, 2, 1, and 1, 3. And now we just want to find like a flow in this graph, right? Like we want to run max flow and check if it's all good. By all good, I mean those are filled and those are filled. Okay, any questions? Yeah.
How did you convert the problem to flow? I didn't.
I mean, it's the same problem. No, like which part? Like my statement is that like fixing those choices is basically. Okay, sorry, I said one wrong thing. So once again, when we have like we did any assignment on those edges which are bidirectional, and now when there was an edge from like some guy who has +2 to some guy who has like -4, we can add like a directed edge here, which and like this says that if we choose like this path, like if our flow chooses this path, we are flipping this one edge between those two to like fix the balances. And for the edges which because like there might be edges which we picked from negatives to positives, we need to add like edge in a second direction so the flow can like undo this choice. And like here in the like upper layer, you put the balances divided by 2. because it means like how many flips do you want to do from this guy. And for this guy, you like put also the balance divided by 2, because it also means how many flips do you want to do from this guy. Just flips mean something different from the upper layer and from the lower layer. Okay, any more questions? Okay, so now my questions to you. Who has any flow in their library? Who has like polynomial flow in their library? By polynomial I mean it does not depend on the weights on edges, like or it depends in a logarithmic way. Okay, I mean, because like, you know, the most basic flow is the one where we like run DFS, right? But it might get really stuck on graphs with like high weights. But when you run DFSs, it's like it's already polynomial. So who has that in their library? Okay, most of the people. Who has something even faster in their library? Okay, so like who has DNIC? Okay, cool. Who has push relabel? Cool. Who has push relabel with some like optimizations? Okay, very little people. Okay, so basically there is this library like KICPL, and they have some crazy fast push relabel, which like can be used to like cheese problems which are not intended to be solved by flow. So it's good to have it. The only thing I remember that there was some like blog post on Code Forces that this implementation is wrong, and like Kosaga or some other like guy, some other LGM provided like a big test case, like 2,000 things, and yeah, here it's wrong. But it gets accepted on like every problem. So, so yeah. Okay, cool. Okay, so now dynamite. So in dynamite, what we did, we have a tree. And there are some dynamites in some of the vertices. Okay, and like we can pick M vertices, and like the fire from them will start spreading with like a unitary speed, and we want them. We want all the dynamites to explode after like a minimal possible time. Right? Any like questions to this statement? Okay. So the first thing we're gonna do, because like we want to place M things to make the like maximum exploding time as small as possible, so we can like invert the way we think, so we can do a binary search and answer. Say we have some K, and we want to check how many places do we need to ignite at least for all the dynamites to explode after at most K. Okay, and with that we can do some simple greedy on a tree. Okay, so for each subtree, what we wanna know. Okay, so like one thing is that when we have some vertex, when we have some like dynamite, and k is for example 100, and like this is the only dynamite here, and we are here, like does it make sense to ignite here? No, because like assuming that there are some parents, of course. No, because like if we are not forced to, then it's not worth to do it on like shallower level, right? Yes, okay, that's one thing, and then oh, okay. So like, what we need to maintain from a subtree? We'll do a greedy thing here, and we need to maintain like two types of informations, because like the state is either there is some dynamite down there, and we don't know, like, and we did not ignite it yet. So we need to like maintain the distance from this dynamite, and as soon as it reaches k, we need to ignite it. And whenever there is, whenever we ignited some vertex in a subtree, we need to remember that we did this. So if we meet like a next dynamite, we still remember that there is like a fire going up, and we also need to remember distance from it, because once it reaches k, it's no longer relevant, right? So the complexity is n log n, because like we do one bin search and then a linear DFS. Any questions?
On this problem,
Yeah.
I was getting like TLE if I did binary search and DFS, and I had to like keep the tour of the DFS and do like
No,
alternative.
I believe you had something like else flow.
Is it not intended to?
No, like not at all. Like
Oh, okay.
my friend got accepted this problem with 2 logarithms, so. But like, maybe LOJ? No, I don't think so. Okay, like if the limit is too tight, sorry for that. But yeah, like on normal competition, it's not intended to force that. And as far as I know, there is no linear solution. So, any questions? Symmetry. Okay. So this one is really easy. I mean, really easy to like talk about it. Okay, so we had a polygon, a simple polygon, not necessarily convex, and we wanted to calculate the number of like axes of symmetry. So, like, what's clear that every like axis of symmetry has to either cut in half some angle or cut in half some segment, right? Any questions to that statement? Okay, so like basically there are 2n candidates to check, and how do we check a single candidate? So this like must mean that like the angles here are good. Those lengths are the same, right? They go into say the same direction. This angle is good. Those lengths are the same. Okay. So how do we do this check faster? We can note down the sequence of lengths and angles, and what I'm saying is that there is an axis of symmetry if this is a palindrome with a center here. Any questions to that statement or? Okay, so like my statement is, let's note down the sequence of lengths of the edges and angles. And my statement is, and like, let it be like infinite, so we don't have the problem with like cycling things, okay? So like, my claim is that if there is a palindrome of length like 2n plus 1 or whatever, or minus 1, with a middle in that angle, it means that there is an axis of symmetry here. Yeah, and we can like check that with hashing or Manaher, like whatever you prefer. Yes.
How can you store the angles without running into precision problems?
Okay, so you can like I think what works is taking. So when you have an angle. Okay, so like the only thing that you need in Manaher is equality comparison. Nothing else, right? So.
You can just keep the dot product and the cross product.
So you
have the integers instead of keeping the
okay, yeah, maybe that works. Yeah, but like I think it's also like it works on like long double. But I'm like not 100% sure. Okay, yeah, and the just cross product does not work, right? Like, yeah, at least it should not. Okay, and if yeah.
There is no problem if, for example, you bisect an angle and it hits another vertex index of symmetry.
You mean overcount? You mean like something like I count this twice?
Yeah, you count this twice and...
Yeah, you just remember that's fine. Like, yeah, you need to subtract it.
Can you always divide by 2?
No, because like, do I always divide by 2? What happens in that case? Maybe, I think so.
I mean, every axis of symmetry will be either counted like passing through a vertex.
Yeah,
perhaps
it seems like that.
the middle of the side, so it should.
Yeah, like, I think I agree. Okay, and any further questions? Okay. Okay, so now the problem distance. We define an operation on a number by like multiplying this number by a prime number or dividing it by a prime. And now this defines a valid like distance function between the integers, the positive integers, and we have some set of values. And for each value, we want to find the closest one to it from this set. And if there is more than one, we want to take the one with the lowest index, but of course different one than itself because it's 0. Okay, so the first thing is to think like, how do we even like what's the optimal way to go from some A1 to A2? And my claim is that like we can, without loss of generality, always go through GCD of those two numbers. Okay, who has any question to that statement? Okay, cool. So that means that like, okay, so how do we solve the problem now? So for each number, for each divisor, okay, so like because for some number to find its like the one that is closest, we'll consider all the possible GCDs of me with another guy. So that basically means we need to browse all the divisors, right? Okay, so we'll do 2 passes. In the first pass, we will like from A1 to all the divisors dividing A1, we will insert that it is possible to visit A1 in some number of steps. Okay, so for example, it is possible to like 100 will tell 5 that it is possible in 3 steps to go to 100. And now for each number here, we'll maintain 2 closest, like 2 best scores. And why 2 best? Because like we don't want because otherwise, if we have, for example, some like big power of 2 and like 3, 5, 7, whatever, then like this 2 to the power of 10 browsing like 2 to the power of 9 might like visit itself, right? And sometimes it might be useful to like go through to the power of 9 if there is like 2 to the power of 8 too, right? So we want to like just get 2 closest ones. Okay, so what's the complexity of and like we do the first pass to like push those inside, and then we do a second pass. Every number looks at all its divisors and like takes the closest one to go. Okay, so what's the complexity? The complexity here is some number of divisors AI over the sequence. Okay, and did anybody pass with this complexity? Oh, that's sad. Because it is possible to do it faster. It is possible to have n log n, because like this is like worse than n log n. Because for example, you can have a number which has a lot of divisors and just have a lot of copies of it, right? N copies of it. So the way to do it faster is to like basically in the first phase, what we only need is we need 2 for each value. We only need 2 numbers with the smallest indices, right? To insert there. Who agrees with that statement? Okay. Okay, so like for the first phase, which means like putting the optimal second parts, we only need for some value, let's say 7, when we have like 7, 7, 7, 8, 7, 9, 7, we only care about those 2 sevens. Because like every other vertex, like every other number, when it is optimal for this number to go to 7, it can as well go to like either of first 2 sevens. 2, because one of them might also want to visit 7, and it will, right? Okay, so this phase is now n log n, and we also need to calculate the result only once for every number, but we need to calculate like 2 best results for each value. We want to calculate 2 closest guys, and this will give us n log n. Any questions? Did anybody have like time limit issues in this problem? Oh, nobody. Okay. Okay, we are near a coffee break, but one more thing before a coffee break. Okay, so let's say that there is a sequence of n integers, n is like 10 to the power of 7, and AI is up 10 to the power of 9. This sequence is like, it somehow already is in the memory, so like we don't really care about the overload from like reading it, or the like even the complexity of reading it, whatever. And what we want to do is we want to calculate, we want to pick some p bigger than 10 to the power of 9, but like smaller than 10 to the power of 9 plus 10 to the power of 8, which will be our modulo. So like we can pick the modulo. It is not given to us, we can pick it. And what we want to calculate? We want to calculate okay, so what we want to calculate, this is XOR. So we want to calculate like sequence of Fibonacci numbers modulo p, and just like get the hash of it, right? So like basically what this means, we want to have this sequence in our memory, and we want it to be to like as fast as we can. I can like I can tell that like the solution that I know has less than 3n multiplications here, but like it is not really like. Please do not think of it as of a like a theoretical computer science problem, because it is not. Like, imagine this is running on a real computer, and you have to like do that with exactly those limits. Like this 3n, like for some bigger values of something, this might not hold anymore, right? Okay. Any questions to this problem? Okay, so that's it. Before the coffee break, so see you in some time. Okay, so the first thing is the solution to this problem. Did anybody come up with something fast? No. Okay. So for this p, we'll pick like any prime p which has like square root of 5 in its like such that a square root of 5 exists modulo p. So whatever. Okay. And now what we're gonna do? So we know that from yesterday that let t be this like square root of 5. That for we want to be able to compute t to the power of n minus t to the power of minus n by no t is not square root of 5. T is 1 plus square root of 5 divided by 2. And here we do t plus t to the power of minus 1. Yeah? Okay. So the main trick here is that we want to calculate powers of some fixed number many times. So what can we do? We can calculate, let b equals square root of our modulo. We can calculate t to the power of 0, t to the power of 1, t to the power of 2, to the power of b, and t to the power of b, t to the power of 2b, t to the power of p. And thanks to that, we can take we can exponentiate t in constant time. Yeah, and that's the trick here. This is sometimes useful when when you have one more, like when you have one logarithm too much in your solution and you are exponentiating the same thing all the time, then you can do this kind of pre-processing. And this is like actually pretty fast. So it's not like constant time, but as bad as logarithm, but it's actually pretty good. Any questions to that part? Okay. Okay, so now we have one problem left, which was spanning trees. And I'm gonna give like a very short editorial now, like an overview of what you need to do, and send you a text editorial later. In this problem, we had a graph. We had some graph on n vertices, where the number of edges between any two vertices, like each vertex has some value ai assigned, it has some value ai assigned, and between every two vertices, the number of edges between them is GCD AI aj. And what we want to do is we want to calculate the number of different spanning trees of this graph. Okay, so who heard of Kirchhoff theorem when it comes to like counting spanning trees? Okay, few people did. So we want to use a Kirchhoff theorem. Kirchhoff theorem basically states that when we take a matrix which is roughly like number of edges in each position, like you get a number of edges between I and j, and something else on a diagonal, not really important now, and then remove last row and last column and take the determinant of that. It's the number of different spanning trees. But the problem is that like the algorithm to compute a determinant is n to the n cube, and this is way too slow for n up to the 5000. So we need to look for something a bit faster. Okay, so instead of calculating determinant, we'll think about calculating a characteristic polynomial of that matrix. And what we know from Cayley-Hamilton, because like the determinant is like the constant coefficient near the characteristic polynomial of a matrix, So what we know from Cayley-Hamilton theorem is that this matrix, when we have some matrix M and its characteristic polynomial P, then this matrix is a root of this polynomial. So let's say we somehow were able to compute M0, M1, M to N. And now, let's think of minimal linear recurrence, which solves this sequence. I mean, this sequence has at least one linear, recurrence, and we may think that if we are lucky, then the linear recurrence is actually this polynomial. I mean, it might be a sum divisor of this polynomial, and then we are screwed. But if this polynomial had no divisors, then we are super happy. Okay, so what we're gonna do now? How would we extract this linear recurrence? We could use Berlekamp-Massey algorithm to do that. But it's all slow now, and we don't actually know what are the odds that we are right. So to fix the fix the odds of being right, what we can do, we can multiply each column by a random number from ZP, and how does it change the characteristic polynomial? So it is multiplied by a product of all those numbers, and with high probability, this means that we'll actually land on a good polynomial. And how do we accelerate this part? Because right now it is n to the power of 4. So it turns out that if we pick a random vector, random vectors A and B, we might actually focus on A, M, I, B, this sequence. So sequence of those matrices multiplied by 2 random vectors, and with high probability, it will be the same linear recurrence. Okay, but how does it help? So it turns out that thanks to special properties of this matrix, because it's not an arbitrary matrix, it has this form mostly, except the diagonal. But we can fix the diagonal later. We can focus on multiplying by matrix which looks like that, and fix the diagonal in a linear time later. Basically, thanks to the structure of this matrix, we can multiply vector by this matrix in n times log n, or n times divisors of n plus sum of divisors ai. I'm not gonna deep into the details, but the second part is basic math reshuffling. Both should pass. Okay, sorry for rushing through it, but I want to talk about other stuff. Okay, any questions to this overview, or I'm gonna once again send the detailed editorial later. Okay, cool. So, okay, let's talk about something else. Let's say we have a number n integers. AI is up to 1,000,000, and we would like to count a number of pairs of indices such that AI and AJ is equal 0. Okay, who knows how to solve this problem?
Can you repeat?
Yeah, sure. We have a sequence of integers up to 1,000,000, and there are 1,000,000 of them. And we want to count the pairs of indices such that when you take those two elements, then it's binary end is equal to 0. So who knows how to solve this problem? Okay. Huh?
It's like SOS.
Yeah. Okay, cool. So we're gonna talk about like this problem and then some generalizations and maybe like another point of view on all those bitwise techniques. Okay, so the first thing is, whoever heard about like the term end convolution or convolution? Okay, not everybody. So the definition is we were like talking about convolutions before, like especially about FFT, which is like basically a plus convolution. So the exponents get added. So what we want to like think about now is let's say that we have like a sequence A, like a vector A and vector B, and we want to be able to calculate a vector C such that Ci is sum over all j and k, such that j and k equals j times bk. So basically, this is like the definition is very similar to like polynomial multiplication, but what happens to exponents is that they get like binarily ended. Okay, and we want to be able to calculate that. Okay, so whoever heard about sum over subsets DP? Okay, so I'm gonna explain. So, like, let's forget about this problem for a moment. And now, what we want to do is we want to calculate. We have some array A, and we want to calculate B, such that Bi is sum over all j's. By this I mean like those are numbers, so we are considering binary masks which are like contained one in another. Okay, so this can be like easily solved in 3 to the log to n by like just iterating over all the submasks for every mask, but it can also be solved faster. So what we can think about? We can think about a graph. We can think about a graph where there are like there are log. Let's small n. Let's big N be equal to the power of k. There are k layers, and each layer has n elements, which are like numbered from 0 to n minus 1. And what we do is we imagine edges from some for every like pair of layers. Here we are focusing on the lowest bit, and there is an edge. There is an edge from from one layer to the next layer. If those numbers differ in a way that adding the lowest bit to the number on the bottom generates like a number on the top. So we will have something like that, right? And for the next layer, we do the same thing, but with another like with the next bit. Okay, so each layer corresponds to doing something like that with with other bit. So now my claim is that when we consider like the bottom vertices and top vertices, my claim is there is at least one path, at most one path between every pair. Like when you take something from bottom and something from top, there is at most one path. Who agrees with that statement? Okay, so first claim is paths are only from subsets to supersets because all the edges add some bit, right, in their representation. And the second claim is like when we have some set of when we have like two masks and then, like on the first step, we are choosing whenever we wanna add a lowest bit or not. On the next step, we are choosing whenever we wanna add next bit or not, and so on and so on. So, like there is exactly one way to choose how to go from from some subset to its superset, right? Who agrees with that statement now? Okay. Any questions? Okay. So what we can think about is we can think about sorting this graph. Like this is a directed acyclic graph. So we could do a topological sort and calculate ADP, and that will give us this sum over subsets, right? In time n times k. But like, of course, this is very impractical implementation. I mean, it has also a very bad constant factor, so we can do it easier. We can go we can think of some like topological order and try to simulate it on an array. So basically, our topological order is like numbers sorted first by layer and then by value. I mean by index. But sorry, by index from highest to lowest. So now what we can do, like how can we implement it? Let's say we have our array A, and now for like every layer from 0 to k minus 1. For every I from n minus 1 to 0, we can do if if I and to the power of L AI plus equal sorry. One more important thing. There are also those edges. My bad. Okay. Okay. So what we do here, we go over layers. We go from back to like from over ints from big to small. And then if some index, if like our index has this bit set, that means that there is an edge from this guy to this guy from the previous guy. So we just add the value of a previous guy, and this is like 4 lines of code, like really 4 lines implementation of sum over subsets. Okay, any questions up to this point?
Yes. Why does the second for have to go from n-1 to 0?
Because
I don't think it does. I think if you can go from 0 to n-1, it will work as well.
Okay, you're right. My bad. Okay, any further questions? Okay. So how does it help? Basically, and one more thing, we can do this like sum over subsets. But what if somebody, like if there was some array A and somebody calculated B, which is basically sum over subsets over A, and we wanted to go back. So basically what we can do is we can reverse the order of all those loops, and instead of addition do a subtraction, and it works. Any like because like again you can consider this graph interpretation and going back. You're basically not losing any information here. So yeah. Any questions with this part? Cool. So we now know how to calculate sum over subsets and inverse sum over subsets very fast. So how does it help us? So let's calculate. Let's have like two arrays A and B, and we want to do this n convolution. So let's calculate sum over subsets on A and sum over subsets on B. This means that like AI is number of indices in like sum of weights in I. Okay, let's maybe don't think about sum of weights. Let's think of those as like expressions, like polynomials, where there is some exponent and like just multiplication just takes the binary end of the exponents. So this is like the number of those x's. It's easier to think about it like that than to about like coefficients. So here we have number of x's such that their I is a subset. Yeah, that their exponent is a subset. Sum over subsets. Yes, it's a subset of I. And here we have those for who like they are in B and their index is a subset of I. So what can we say about A prime I times B prime I? So this means we are choosing something that is its element. Like we are choosing some x such that its exponent is a subset of I in ARI, and in B we are also choosing some x such that its exponent is a subset of I. So I'm saying that this for sure must be also a subset of I. Like if we combine both of them, then like the end of two numbers for who they are like product of two numbers which are subset of I is also a subset of I, right? No, I mean end. Sorry. So if like because like end is a set intersection. So if A is a subset of C and B is a subset of C, then it basically means that A product B must also be a subset of C, right? This is what end does. Okay, I see what I'm doing wrong. Sorry for the confusion. Let's calculate not AND convolution but OR convolution. My bad. But it also holds for sum and OR, right? Okay, so but now what I'm saying is that like those are the only choices such that if we choose some index from like something from A and something from B, their OR will be a subset of I. Because like if we choose something which is not a subset of I in like either of those, then their OR will like go out of this I, right? So I'm saying those are all the ones such that their intersection, sorry, their sum is a subset of I, and all the ones and only ones. So that means that when we consider array C'I, which is like defined in such way, then I'm saying that C' is sum over subsets of C. Right? Thanks to the property that here we have we contain all the ones for which it's OR of them. Okay, and how do we do that with AND? So we can do instead of sum over subsets, we can do sum over oversets. Sorry, sum over supersets, and this like inverts the logic here, and here, and it's the same thing. Like basically, we can think of OR and AND as the same operation, but like what OR does, it's like OR is an AND, but we are ending zeros, not ones, right? If there is at least one, then OR produces one, and for AND, if there is at least one 0, AND produces 0. So like this is the same operation, but the values have different labels. Okay, are there any questions up to this point? Okay, so so that means that like with this knowledge that we can solve the problem. We have array A and array B, like AI, BI are up to a million. We want to calculate the number of like IJs such that AI and Bj is equal to 0, right? We can just do like count the values in both arrays and do an AND convolution over them and like just get the 0th element of the resulting array. Okay, are there any questions up to this point? Okay.
Sorry.
Yeah.
But then the AND convolution uses the same logic as the OR convolution.
Yes, but instead of sum over subsets, you do sum over supersets. So it's like the other way around. Instead of like pushing the value into all the supersets, you want to. So like you basically invert the edges in this graph and do it in a reverse order. Okay. Yeah?
Do we do something similar with OR operation?
With XOR operation? Yes, we can. Well, later. Okay. So we can do that. Okay. Now let's go to something more interesting, which is we have an array. We have some sequence AI, and we want to count number of subsequences of this sequence, such that some like A T1 and A T2 and A Tk equals 0. Okay, and we have like n up to a million and AI up to a million. Okay, who knows how to solve this task? Cool. Okay, so I'm gonna tell, because there is like, I know 2 solutions to this problem, and I'm gonna tell the lesser known one, but in my opinion it's better because it generalizes to harder problems. So let's think of a stupid brute force. What can our stupid brute force be? So let's imagine array Bi such that bi 0 is equal, bi n minus 1. N minus 1 is a full mask, right? So bn n minus 1 is equal to 1, and bi ai is equal to 1. Otherwise, it's equal to 0. Okay? So let's now say that this is like the end convolution of two vectors. So what I'm saying is that the result is b1 convolution b2 convolution b3 convolution bn small n. Who agrees with this statement? Okay, so I'm gonna elaborate. So basically, when we are considering an ordinary like FFT convolution, where we were picking something, where we were able to like pick some subsets, what we were actually doing, like we were expressing this choice by a product of polynomials. So here we can think of it that we have like a single bracket, which is x to the power of n minus 1. This is a full mask, plus x to the power of ai. So that means that in if bracket, we can either choose a full mask, which says like end with everything, so like do not change our result, or we can pick the element from the sequence, right, which ends the exponent by ai. So now like when we take this product over ice, my claim is that the result is like zeroth element of this convolution, right? Any questions to this part? Okay, but like this is obviously not this solution like for single b. Okay, how would we do that? If we were to do it like naively, we would do something like let's denote by like t is like t a produces just like sauce. Okay, so but like I will write this a lot, so I want a single character. So let t of ta do a sauce, t minus 1a be like a reverse sauce, and single dot be a pointwise product. So we are multiplying at each position. Okay. So how do we take a product of? How do we actually take the end convolution? Okay, so this is not sum over supersets. Okay. How do we take a convolution of two elements? So what we are doing t minus 1, yay, tb. This is what we do to take a normal convolution. Let's say we want to take a third element. Like we want to also do a third element. What will we do? Okay. So who agrees with this? Who has some question to this part? Okay, so what we can see is that it doesn't make sense to do that, right? We are like applying t and inverting t. So we get to something cool. We can like calculate a convolution of multiple vectors by just applying the transform on each of them, then multiplying and applying inverse transform just once. Okay, so how can we use that? We have to think about how we need to think about how does t of bi look like. So like we need to like do some further analysis on like how those transformed BIs look like, and we want to like compute a pointwise product of n BIs faster than naively. So our like this convolutional tool will be just like a proving tool to prove our calculations, but we're actually not gonna calculate convolution n times. Sorry, transform n times, right? Because it's too slow. Okay. So how does T for BI look like? So it's sum over supersets. So my claim is that everybody is a sum over supersets. So everybody has n-1 as its superset. So they get at least one. And some guys have this guy as its superset. So basically what I'm saying, this vector is so we have 2 if let here be something like j I is equals 2 if I is a subset of j and 1 otherwise, right? That's how the like transformed vector look like. And any question to this part? Okay, so how does a product of n such vectors look like? So we basically just need to count how many ones, like how many 2's are in each column. And there is 1 2 in each column for every guy who's a superset of us, right? So basically, what we actually need to do is to calculate some, let C be sum over BIs, and we do T, C, and then apply pointwise 2 to the power of x, and then go back, and it's our result. Any questions to this part? Okay, so like quick overview of what we did. We are actually wondering how those elements, like those T's look like for this specific type of vector. And thanks to the specific structure, we are able to have like a closed form formula for a pointwise product of all those n vectors. And thanks to that, we were able to like just produce a ready product without naively multiplying, and then invert it. Yeah, and it is just like by a coincidence that to calculate how does this ready product look like, we also need to use T. But it's just like for calculations. It's not the same type of usage of T. Okay, any questions here? Okay. Okay, so now I'm going to talk. Yeah. Sorry, I cannot hear you. Which?
How do you go to the sum over superset form and vice versa? I didn't get that transformation.
Okay, but you get the sum over subsets. So, like I'm saying that sum over supersets is let's imagine this graph from sum over subsets and reverse the edges.
That was the other part. I checked the graph.
So you want me to repeat sum over subsets?
Yeah, if not, I can explain.
Okay, so so we are considering a graph which consists of n times k vertices, where n is like some power of 2 and k is its logarithm. Okay, so now for like 0th layer, we are considering all the edges from some guy to the next guy, if like adding 0th bit will make us this next guy, yes? And we are also considering edges which do nothing from everybody. On second layer, there are those edges which do nothing, but also the edges which consider the addition of like a first bit. So like only if this guy has no first bit, then it has an edge going to a version which does have the first bit. Okay. Do you understand how to like construct this graph? Okay. So now my claim is that from some index I to some index j, there is a path only if I is a subset of j. Because like we can only add bits in like binary representation by walking in this graph, right? And I'm also saying that there is exactly one path if it is an index, like if it's a subset. Because like let me draw that. Like when we are on a 0th bit, then what we see is that we need to insert the first bit, like pick this diagonal edge, because otherwise there is never a later moment on which we can insert this bit, right? And like this argument applies for every bit. So like there is a unique path from any subset to its superset. So I'm saying that like doing just like ordinary relaxation DP, so like iterate over all the edges in topological order and add there. This like calculates sum over subsets, right? You get it now? Okay, cool. Any further questions? Okay. Now, like, one thing here is that okay, what we can do, what we can like also do with this trick is we can do a GCD convolution. So instead of taking end of two indices, we can take GCD of two indices. And like, how to do that? Just do sum over divisors or sum over multiplies. And why does it work? Because this is basically the same operation when you really think about it. Like GCD basically means for every like periodic exponent, so like power, so like the exponents near a prime number in the factorization, you take a minimum of them when you do a GCD, right? So it's like a minimum on a vector of bits. So like the same arguments apply for like every step. Okay. And also we can do like okay. I'm gonna talk now about how to do XOR. So who heard about XOR convolution before? Okay. Who can say that they know how it works? Wow, cool. I expected number of hands to be 0. Okay. Who like knows how it works? Like because I think there are like two ways. Okay, there are at least two ways. So one way is some meaningless sums which give no intuition, and one way is like Kronecker product and things like that. Who knows like the Kronecker product way? Wow, one person, but not 0. Cool. Okay, so I'm going to talk about Kronecker product and what can we do with this, because what it really gives us, it gives us a general way to design convolutions which do like different things on different bits. Okay, so what we like. Okay, let's define first a Kronecker product. So let's have some matrix A times like some A, B, C, D. Let it be empty dot. It's a Kronecker product. Then what it gives us is okay, so like this is some matrix, those are numbers. And so what it does, it like multiplies the dimensions of A by 2 and like pastes A 4 times and with some coefficients from this matrix, right? And it also works for like different dimensions of this thing, but it's a notation hell basically to like. So I'm like just showing you on an example, yeah.
Multiplies the order of the matrices.
The order, the like size, yeah. So like this matrix has its like height multiply as like its height is a multiple of height of this and height of this, right?
Okay.
Yeah, you see now? Okay. Any further questions? Okay. So okay, and now another thing is that let's say and that we wanted to do a XOR convolution. So like as expected, everything, but instead of OR and or whatever we have XOR. But we wanted to do it on a 2 bits, sorry, on a 1 bit now. So let's think of it as we have a vector of like 2 elements. And what we want to do is like we want to go the usual way as it is with convolutions. So we want to find some transformation t such that t of this times pointwise times t of this t minus 1. Okay, so like we want to find some such transform that it holds like that. That this like holds. That this is the like whatever convolution we want. So in that case, it's XOR convolution. So in like it makes sense for it to be a linear transform because like actually all the previous transforms are actually linear. So like FFT is a linear transform. This sum over subsets is also a linear transform. So how can we like design a linear transform that works on 2 elements? So it turns out that somebody did it for us already. It's a Hadamard matrix. I think it's like that. Let me Google that. Okay, actually. Okay. It's this matrix. So let's skip the part. How do we come up with this matrix? What we know is that for arbitrary 2 vectors of size 2, this helps us to have XOR convolution. We basically need to do like just t a t b t minus 1. Oh, what's important that like this matrix is also invertible. This is like a requirement for it to be true. And like okay, so like maybe a very short part. How does one even think of finding such matrices? So basically, what we need to do is we need to think that we have some A, B, and so here we have just a second. Okay, so what happens here is that like here we have input vector first, here we have second input vector, and here we have a like resulting vector of XOR convolution for like those arbitrary two vectors. Because like XOR 0 is for AC and BD, and the other pairs have XOR 1, right? So we want this to hold for some choice of x1, x2, x3, x4. So we can like evaluate this expression symbolically, like just multiply everything on the variables, and then try to like come up with a substitution such that this works. But like the only thing we need to care about is that those numbers need to be this matrix has to be invertible. And this is like a general way to come up with convolution on some small groups of elements. Because like what actually happens in XOR convolution, there are actually log convolutions of size 2 in each dimension. So this is what we need to do in one dimension, and then we can like just scale it. I will tell just in a moment how to scale it into multiple dimensions with a Kronecker product. What we wanna do is we wanna find such matrices. And it sometimes requires a field extension. Sometimes it's impossible. This is like in general. There is no like auto solver. You need a brain here. Okay. So we have this matrix. Cool. One can like substitute it here and see that it works. Cool. What we want to do now is we need to like think about how does okay. So my claim is that if we want to have a convolution consisting of like multiple smaller convolutions in many dimensions, and we have convolving matrices for like each of the dimensions, my claim is that our convolving matrix for the full convolution is A1, Kronecker, A2, Kronecker, A3, Kronecker, AK. So one can observe this, for example, when we are doing sum over subsets and we are doing OR convolution. So then we can pick a matrix, this matrix, and now let's think of Kronecker product of like cave Kronecker product of this matrix. By the way, it's a really like notation hell to describe what's cave Kronecker product of some arbitrary size matrices. But so what this matrix does is let's. I actually don't remember if it's sum over subsets or sum over subsets supersets. We'll discover in a moment. But it doesn't matter. Like it's the same thing actually. Like up to some rotations or symmetries. So what happens here is that we have some indice I and we have one. We have some indice J. Okay, so we have one only when I is a superset of J, right? On those 2 bits. Because like the only one case when it's not the case is when J is equal to 1 and I is equal to 0. Then J is not a subset of I. So how it transforms our vector? So for like 0 we get from 0 and 1, and for 1 we get only from 1. So it's sum over supersets, right? Now think about what happens when we take a Kronecker product of this matrix with itself. So we get 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, no, sorry. Here we get only zeros. Okay, maybe let's write it down in a different way. It's 0 times that, right? So here are only the zeros. Okay, so now let's think what it does with the input vector. It's like for what are the like numbers here? 0, 1, 2, 3. 0, 1, 2, 3. So what we can think about is that like first choice of the like we might think of a position that we are first choosing like 1/4 of a matrix, and this choice corresponds to a choice of bits in like upper index and like left index, right? And then as we are descending, we are all the time choosing like 1/4 of this matrix and choosing some bits. So what this matrix says here is that if you choose 1 here and 0 here, no matter what you choose later, like you do not contribute, right? Because like it's already not a sum of subsets. Yeah, and so like this, what this Kronecker product basically does is it stacks independent transforms to like produce a bigger transform, which corresponds to a like joint convolution in each dimension. Okay, cool. So thanks to that, we can just like stack this matrix and have XOR convolution that way. Okay, and now what's the like algorithm to stack those transforms? So it's exactly the same as you do a multi-dimensional FFT. So like what you think about is that first you have like a big let's say you have this like matrix which is like divided into 4 parts, which are also divided into 4 parts, but this is like all divided by a Kronecker product. So what we do first is we like divide this vector into and we have like this guy, this guy, this guy. We divide our vector into like blocks of size 2, and each of those blocks gets multiplied by this guy. So it's like the deepest part of the Kronecker product. And now we like divide into bigger blocks, and then they get like multiplied by this like bigger by next guy. It's like those 2 elements get multiplied together by this. Those 2 elements get multiplied together by this. It's like the same thing as with stacking FFTs. Okay, cool. So this gives us like a very general way to stack like arbitrary convolutions. But what's sad is that you actually cannot do much with this. I mean, besides like XOR or AND are their generalizations. So for example, we take a max, and like for example, we allow elements up to 3, or we take a sum, or we take a sum modulo. I think there are no more meaningful operations which we can do. I would like to be surprised. If somebody knows, I will be happy to hear that. Okay, so now some problem.
Can I ask a question?
Yeah.
The matrix is transforms a vector into a sum of success.
Yeah.
What does the other matrix do, like the one which was generated with 1, 1, 1 minus 1?
Yeah. So okay. So it turns a vector into a vector of. I can write it down. It turns some vector A into B such that BI is sum over J AI times minus 1 to the power of pop count of I and J.
So if it has a number of bits, it is subtracted.
Like if the intersection of them, like if the intersection of the index we are looking at and the index that's like goes there.
Okay.
Yeah. Okay. I'm gonna like rush for it because there is one more problem I'd like to talk about. So this problem is from some Polish Olympiads. I don't remember the number. We are given n elements AI up to 10 to the power of 6, such that sum AI n is 10 to the power of 6. Sum of AI is up 10 to the power of 7. And we are given some number k. So, and those are like piles of stones. And what we wanna do is we wanna pick some number of piles of stones divisible by k. K is up to 20. You wanna pick the number of piles divisible by k in a way that like this game is winnable by a second player. So it's a well-known fact that we are actually looking for like the subsets of size divisible by k, such that their XOR is 0, right? Okay, so this was the problem on the Polish Olympiad in Informatics, and at some point I tried to solve it, but I didn't really know what this thing has to do with the problem, so I ignored it. And I can solve this problem, which is a bit harder. So the previous problem was actually some like pretty easy DP, using the fact that like the sum is small, but this problem gets really tough. Yeah, and like I'm the author. What we're gonna do here is like we want to do a two-dimensional convolution. Where like okay, we want to actually calculate sum over product over 1 plus x to the power AI times y, where like x is a variable of a polynomial such that like their exponents XOR with each other, and y is a variable of polynomial such that y to the power of 20 is equal to 1. Yeah. Y to the power of k is equal to 1. So like thanks to that, our like choice polynomials maintain XOR of our choice on x variable and like size modulo k on y variable. Any questions to this part? Okay. So now what we need to think about? We want to do this like the same trick as we did with this end problem. We want to like see how does t for this vector, this like two-dimensional vector look like, and because like it's two dimensions now. One dimension is like x-axis, and second dimension is y-axis. And we want to see how does this look like for how does t look like for that, and calculate it fast. So what we can do here? Okay, how does this like look graphically? So let this be like x-axis and y-axis. So we have one, so it's like one guy here, and we have some guy here, right? Because here we have like two-dimensional convolution, so like one dimension is XOR, second dimension is just sum. So we could do some FFT stuff on like one dimension, and XOR like Walsh Hadamard on another. Walsh Hadamard is like this thing, but we're not gonna do FFT on like this dimension. We're gonna do like a naive multiplication on this dimension. It will help us. So like, how does T of this look like? So let's recall this formula that AI is BI is sum over all AIs AJs times -1 to the power of pop count I and J. What's the time? Okay, we have 5 minutes. Okay, so how does this look like? So basically, here, like on this bottom row, we always get ones because, we may think of it that like it's a linear transform. So the part with y stays with y, right? And the part without y stays without y. So like with this formula, when you have a pop count of 1 translates as like x0, y0. So when we have a pop count of 0 and something, it's always 0, so it's with a coefficient 1. So like this one gets pushed everywhere with a coefficient 1. Okay? And now we need to think what happens with this y. And this is like actually the tricky part. What happens with this y is there are somewhere ones and somewhere minus ones, right? Okay. So now for a moment, let's think how will our like final product look like. So basically, what we are doing is in each column we have some polynomials which depend on y, right? And we are like multiplying them in this y dimension, just like naive multiplication. And all of them are, and like this product is of form minus y plus 1 to the power of alpha times y plus 1 to the power of beta, right? Because only such expressions can be created in this column. Okay, so we know one thing. Alpha plus beta is equal to n, right? Okay, we need one more linearly independent expression of alpha and beta to be able to like get both of them. So it turns out we can get the difference. And now, how do we get the difference? So we want to know how many times what we're gonna do is we're gonna, as in previous task, count those like AIs on a vector and do a fast Walsh Hadamard transform, like this transformation T on this vector. So what it is a sum of all those like second rows over all those elements. So that means that if at some position there are like there's some amount of ones and some amount of minus ones, this is like we get alpha plus minus 1 times beta at this position, right? Because like all the minus ones are with the coefficient -1 because like themselves, and all the ones are with a coefficient 1. So when we just count the input sequence on that and do a like fast Walsh Hadamard transform on that, we get like the sequence of differences of those exponents, and now it's like a very standard part. So we just need to calculate the powers of those polynomials, but it can be done in like times in n times k, because like when you have a power of like you have some power of this polynomial and you want to calculate the next one, you need to notice that you are multiplying by only like the polynomial is very sparse, so you are multiplying by only like two new things, and now we could just like for each point, multiply two polynomials and to get time like n plus n times k square, and then do a fast Walsh-Hadamard on that, so like times log to go back. But we can go faster. So what we actually only care about is we only care about like this lower row of the result because like we only care about modulo equal to 0. And since Walsh-Hadamard is a linear transform, that means that we only need to take like this lower part of a product of those polynomials, because the part that is with y will stay with y after the transform. So we can get rid of this squared and get plus n log, because that like we do not need to run a full like inverse transform on all the rows. We can just run the inverse transform on like the most bottom row which we calculated, and yeah, and that's it. Okay, any questions? Okay, cool. Thank you then.